plasma, dielectric, or whatever, right? So, first, somehow the equations are the same. Okay, good. Only 7? Of course, now, the thing is, like, you think about it, like, you have this electromagnetic wave in plasma or media or insulator or whatever, and, you need to know the currents, right? That's the game. You tell me the currents and then I solve, right? But in this case, right, you're in media and all those particles are moving around, right? So it's sort of hopeless to say what all those particles are doing, right? So you need some other information in order to do anything, right? So that's just the truth, right? So you need to somehow tell me this. So good. So how can we do that? So, well, first you need some physics intuition, right? So for an insulator, right? We have this picture, which you probably learned as an undergraduate. If I have like a parallel plate capacitor, and this is some electric field here. Also, then we have this picture of the dipole moment. We somehow polarize the media. So you can kind of take that. One route would be to sort of take that physical picture and sort of come up with some ideas of what this current could be. Okay? I will take a little bit more mature view, okay? Which is that you basically you don't really know what these currents are, and so the only thing you can really do is sort of write down everything that's possible, okay? And of course, if you've written down everything that's possible, then it's got to work, right? So that's, of course, usually it's write down everything that's possible. That's not so helpful, okay? So, but here, a lot of things can help. Okay, so for instance, key points. So of course, you want to use symmetry a lot. I mean, symmetry will constrain what it is. So we're going to talk a little bit about what are the symmetries of electricity and magnetism. Okay, there's some other things you want to keep in mind. Okay, so of course, if the other one of the main things is of course it's very long wavelength. You have some wave. Okay, this is even shorter and faster than I would initially consider. But the typical wavelength here is hundreds of nanometers. Say, I don't know, some hundreds of nanometers. Right? And this typical spacing between particles is angstroms, right? So it's not like that's why in some sense it's a little bit misleading, right? Because it's not like you can actually resolve dipoles there, right? You just see some coarse grains, sort of. You don't really see what's going on inside the microscopic details at all, right? Waves are just so long, you don't even see anything that happens in the medium, right? And furthermore, they typically happen so slowly that, so to say, these atoms respond nearly instantaneously to the changes in the field. Okay, so we're going to use that. Okay, so that's the first number point. Number two is, of course, typically the electric field is very weak, okay? Weak. That also helps, right? Because just think about it. I mean, a typical external electric field, say it's strong laboratory field, right? You know, a kilovolt per centimeter. That's a pretty strong field, okay? 1 kilovolt per centimeter, right? It's 10 to the 5th volts per meter. It's a strong laboratory field. And just compare that to an atom field, okay? E atom. Okay? So the typical energy electric field is like, 13.6 eV per electron charge, right? And the size that we're talking about is 1 angstrom. Again, so 1 angstrom, typical atomic size, right? So the typical volt per meter is 13.6 eV per charge. These cancel, so as you get 13.6 volts per angstrom, right? Which is 10 to the 11. So, of course, a typical atomic fields are just sort of vastly larger than what we're talking about. Right? So you're going to use that as kind of an expansion parameter, okay, when you start to think about the type of currents. Okay. Okay, so now, have here. Okay, so let's talk then a little bit about the symmetry part of it. Okay, so needless to say, so let's talk about the symmetry part, right? So first, some mechanics. Okay? And we're going to be talking about parity first, parity and time reversal, and later time reversal. So first parity. Okay. So what do we mean here? Right? So if we say that under parity, the coordinate, you have some coordinate of particles, right? So under parity, we get a new solution, right? Which is related to the old solution via change in sign of the coordinate. So just invert the thing in the mirror, okay? And similarly, the momentum, you think about inverting yourself in the mirror, right? The momentum is also reversed, so P of t goes to some new P bar of t minus P. Okay, good. But other things like the angular momentum, yeah, this is, of course, R cross P, right, goes to some new angular momentum, which is actually the same. Okay, so far we just said, how we map the coordinates of momenta, right? We haven't really said yet what we mean by it to be a symmetry, okay? So what we mean by it to be a symmetry is that, under this map, if you had a solution to the equations of motion, then under this map you get a new solution, right? So that's kind of a statement. So let me see. So if I have an ohms, so if x of t and p of t satisfy, okay, so that dp dt the force, when you think about the forces, there's some, think about like Coulomb's law, there's some function of the coordinates and positions of all the momenta of all the particles. Okay? So let's assume that x and t and p of t satisfy this, okay? Okay, and now if it's a solution, right, then what we say is that, of course, x bar and p bar are also solutions. Okay? Then, if parity is a symmetry, so that leads to some requirements in the forces. Of course, like this, right? Okay, and so, well, exchanging, using what you have there for p bar, it says that minus dp dt. And so, well, okay, since dp dt satisfies this, right, you get some requirements on the force, right? So the force, minus x and minus p is equal to minus f. Okay, so if you want parity to be a solution, a symmetry, you require that the force be odd under inversion of the coordinates. I should say. Okay. So, I don't know, f is odd under inversion of the coordinates. If it's a symmetry, right? There's no requirement. The forces are where they are. Okay? If it's a symmetry. In general, the force may not be, odd over there. So, just an example. Typical case, right? Where parity is a good concept, right? If I take Newton's law. Good. Okay. Okay, so that would be an example of a force which satisfies this. Yeah, go ahead.
Yeah, so I mean, I don't see how this can possibly break down if force is dp dt. Like, how, I mean, how could it not be?
Simple. I mean, so if the force is not odd, right?
Okay.
Then there's no relationship between the solution in one place and the inverted solution, right? Which is saying that the parity is not a symmetry and there's no relationship between one and the other, right? It's only if the force is odd under inversion that there's a relationship between the solutions, right? So, right. Of course, we have examples of forces, weak forces, where it's not, right? And then the solution, it doesn't tell you anything about the other, right? Right. Okay, so time reversal. Time reversal is somehow the same logic. Okay, so if I have some solution x of t if I consider it time reverse solution, but not clear it's a solution yet, we define some new x of t, which is related to the old one by inversion of the time coordinate. Okay. The same thing with the momentum p of t, except think about reversing time, right? And the velocity kind of flows in the opposite direction. So you would get a new momentum, which is minus p of Okay, so, t is, parameter, right? So we have a solution. It's valid for all times, x of t and p of t. And we're asking whether this new inverted x of t and p of t, right, are also solutions. Right? Okay. So again, we do the same thing, right? So we ask if these are solutions. So well, first of all, okay, x and t are p of t are solutions. So dp dt of t is equal to f of t and x of t dp of t. Right? That's given. That these are solutions. And now if I invert, ask if x bar and p bar are solutions. So t is just a parameter, right? It's just running from minus infinity to infinity. Right? So we want to know if this thing is a solution. Okay. dp bar dt is f of t, x bar of t, p bar of t. So that's saying that this new positions and momenta are also solutions, right? To the equations of motion. So then if I sort of write down what this p bar is and x bar is, right, I get that this is minus dp of minus t, right? dt is equal to f here of t and x of minus t minus p of minus t. Okay. And so, well, let me do like this. Let me put here minus t. Here, put a minus. Okay. Okay, so good. That's plus. Okay. So again, like t is just a parameter. It runs from minus infinity to infinity. You just replace it with a new parameter, right? This equation says that f of p dp dt of t is equal to f of minus t and x of t, p of t. Okay. And so now a comparison would show that the forces need to satisfy certain requirements. Okay, so compare these two. You get a constraint that if the symmetry, if time reversal is a symmetry, okay, then f of t x and p is equal to f minus t x of t minus p of t. Okay, so, well, okay, so that's a requirement. Somehow it's going to be a symmetry on good. Okay, and if the forces don't obey that, then it's not a symmetry, right? Of the equations of motion. So that's pretty subtle stuff, right? This time reversal symmetry. Okay. So let's give an example of one force which doesn't respect time reversal symmetry. Okay. Very common, right? So for example, you could drag force. Well, okay, so I have a particle that's slowing down due to some viscosity or something like this. So then, clearly, if I take, if I look at this requirement, right, it's not an explicit function of t, right? So it clearly doesn't satisfy this. Minus p is eta plus eta, which is not equal to p. Right? So in such a case, we clearly have that time reversal is broken by the nature of the forces. Right? Okay, and it's not going to be a good symmetry of the solution. So. Good. All right, so it's sort of very much parallels here with electricity and magnetism and parity. Okay, so first now let's look at electricity and magnetism.
Just in the left-hand side, in the middle of the chalkboard, you exchange t for minus t in dp/dt, right? But then, isn't the result still evaluated at minus t?
So again, in this line,
Yeah.
right?
Yeah.
Let's do it again one more time slowly. So it was somehow like this. Okay. And now all I'm doing is say, okay, derivative with respect to t is respect to minus t. So I make it a plus. And now I say t is just a parameter, say minus infinity or infinity. Just change its name. And this was here. Right? So I just change its name. Right? I just replace everywhere t minus t, t with minus t. Okay, and that's why I put there this minus t.
I know why I was confused. Why is dp/dt at minus t minus dp/dt at t, the first step?
Yeah, so that's sort of this somehow the statement. So what is p bar, right, of t? So p bar of t is minus e minus t. That means over time reversal.
That's where, sorry.
Yeah.
Okay, so then so I agree with this statement, but then if you take the time derivative, shouldn't you add in then another minus sign?
No.
Are you not switching the t
This
to
is,
the bottom?
I get some new coordinates and momenta. Right? So the picture would be somehow like this. Let's do here time in this position. So suppose I have harmonic oscillator, right? This looks like this, okay? Something like this, solution, right? And now under this map, okay? Right? So we just reverse the momenta, we take this solution and we get something that looks like this, right? Right? And we're asking whether this thing that we've just constructed in this way is a solution, right? So this is some new x of t, x bar of t, p bar of t. Same equation of motion. You're just asking, is this true? All right, under what conditions is this true? Right, that this satisfies this inverted thing, right? Satisfies the equations of motion, right? And then, go there and you find as consequences that forces should be this, right? Okay. So, yeah, it's all stuff, okay? You have to go through it slowly and ask yourself, okay, what do I mean? Right? And if you think about that, you're trying to have a relationship between solutions, then you make progress. That's the non-trivial thing. You have one solution and you get another solution from the map. That's what we mean by symmetry. Okay. Good. So let me-
Is it true that all like real forces are time reversal? Like this drag force is sort of something like kind of, but it's like a model kind of, and not like
Kind
a
of model? Oh, okay.
I don't know what
It's
it
a
was.
model that agrees with the experiment,
Yeah.
right?
Yeah, right.
And then we're asking, does this system of equations with this force, right,
Mhm.
have a time reversal symmetry? Answer no, right? Okay. So there's a long story there in statistical mechanics. So you say the microscopic forces are time reversal invariant, then you can say, you can develop some consequences in statistical mechanics, and then you get somehow that there should be some extra term there, which is some noise term. You could relate, you can use the microscopic, in fact, the microscopic equations of motion are invariant under time reversal to derive what's called fluctuation dissipation theorem, which says that the random forces should be equal to 2t times the time. So that's maybe some long story in statistical mechanics of great interest, kind of outside of our purview here. Okay. All right. So there is consequences that the microscopic forces are time reversal invariant. Okay. Let's get back to EM and parity though. Okay. EM and parity. Okay. So. Let's first consider parity symmetric theory. Okay. Now, of course, you tell me how the currents, if you have some external currents which you're specifying, you have to tell me how to change in the parity, right? Because EM doesn't know, right? You tell me the currents, and you also need to tell me how it gets mapped under parity. So normally, when we take a parity symmetric theory, okay, on the currents and charges, okay, are, say, the charge. Right? If I invert my coordinates, I normally say that it's unchanged, right? Somehow. If I invert my coordinates, somehow the charge is the same, right? Okay, so that's parity. Okay. So the current charge density and current. Okay, so current is like charge times velocity. If I invert my coordinates, then velocity changes sign, right? So the current should be odd under parity, okay? So we would expect somehow that rho go to rho, okay? And J go to minus J. And or at least let's assume that they do. Right? And you put there the arguments, so the rho is a function of, right? So under parity inversion, we get the following. Okay. I was calling this rho bar t into x. So we get some under inversion. So it's a non-trivial thing, right? I mean, you have some currents, right? And you say, let me replace it with some new set of currents, right? Rho bar of t and x. So we have some old charges and old currents. We replace it with some new currents, rho bar of t of x, and j bar of t of x, which are related to the old ones in this fashion, right? And that's sort of what we mean by inversion, okay? And now we look for new solutions to the electricity and magnitude equations of motion. Right? So solutions, right? Okay, then we want to find some new solutions. Like that. Okay, that's just our goal. We want to find some new solutions, okay? And can we relate the new solutions to the old solutions, okay? And so if parity is a symmetry, then you can, right? So let's see. So our equations of motion, good. Right, so we're trying to solve now these equations where J bar is related to the old J like that, right? And so, well, you can just check. Okay, so look at this equation slowly. Okay, so if E and B solve the equations, the original equations, then you can just check that the following P bar of T and X is equal to minus E T and minus X, okay? And B bar T and X is equal to plus E X. Static does the job, okay? Solves the equation. Equations. So that, in that sense, we'd say that E is odd. Odd. And E is even. Parity. Good. So, well, okay, so let's just check maybe just very quickly see that. Let's look at this thing. So imagine let's look at this equation. Right? So, well, so curl of B bar, let's just check it. Curl of B bar, okay, is equal to minus the curl of E of T and minus X. Okay. J bar is equal to minus J T and minus X. I'm just looking at those terms one by one. So this one, they should all change sign. Okay. Right? And so here E of T bar, E bar of T and X. Right, the time derivative is just the minus. Okay. So essentially, under this thing, everything, we know that for any value of x, right? For any value of x, we have here, we just have this thing. Okay, So the solution, the fact that E and B and all satisfy the original equation of motion implies that this is also true. Right? So if you have, since everything changed sign here, right? This becomes minuses everywhere. Okay, minuses without any bars. Okay, so we can just erase this thing. It holds for all x, right? So that's fine.
Should this be like a minus x on top, like e of, right by where it says solves equations? You have plus b t of x.
Solves the equation.
Yeah.
It should
And
be,
minus
of course,
x.
minus.
Okay, and also, are you switching the sign then on del, on the del operator? So it's like,
So,
is this?
What am I doing? I want to, of course, do like, of course, what I want to do is to say I'm taking the derivative with respect to x, and now I take the derivative with respect to minus x. Yeah, it's better. But I have to consider minus. Good. That's better. Okay. Okay. Okay, so finally, let's do this time reversal. So time reversal goes through very much the same way. Okay. Okay, good. The time reversal. Okay, so again, we take the charge to be microscopic currents and charges. Okay. Okay, to be even under time reversal, kind of reverse the direction of time, we take the charge to be even, okay? Rho t of x, right? So we have some charge density. We consider a new charge density, rho t bar, sorry, t bar, t in x, right? Which is equal to minus rho, sorry, plus or minus t of x. So we, to have some old charge density, we consider a new charge density. And similarly, we consider a new current, J of t in x. So it's kind of goes to some new current, J bar of t in x, which is related to the old one, time inversion. So, go back here. Put that in my bars. Okay, so again, the strategy is the same, so it's still on the board. So if E and B and T and X are solutions, in the uninverted case, we look for some new E bar and B bar, which are solutions in the inverted case, right? And in this case, of course, you look at it again, right? And you see that if E bar, oh, it's still on the board. So now we have to switch the signs. So if E bar is plus here and minus x, okay, and this is equal to minus. So let's just check that this works. I mean, say, so you can take any equation, but let's say take this one. Right? So of course, you know, curl of E bar. Okay, this becomes the same, right? Curl, so by definition. Right? And the time derivative of B bar of T and X, right? Okay, is equal to, well, B bar is time derivative. Yeah. And definition, right, plus, right? Okay, and B is odd. Minus sign there, right? So B is odd under time reversal. And so now you can replace it with the parameter m minus plus derivative of minus t e minus t. Okay, good. Which gives you a plus. Okay. So okay, so you're left with the statement somehow that this is even. Okay, so this equation so again, t is just the parameter. Let's replace t with minus t. And that's it. Okay? Good. All right. So, okay, so I hope to, so I summarize these things online so, you know, you could ask yourself whether, you know, just, let's just maybe say it in words, right? So, under parity, right? E is what? Even, right? Even under parity. Think about an electric field. Okay, even under time reversal. Okay, and okay, E is also odd under parity. Sorry, did I say it right? So E is odd under parity, and even under time reversal. B is even. Okay, good. So now we got that out of the way. Okay, let's get back to solving for constitutive relations. Okay. So again, we're going to take the current, free current. Okay. Usually we break it up one, which is a function of the external fields, and one which we specify. So some medium currents and some external currents. Okay. The external currents I tell you, or you are given to you at the start of the problem. Right? They're known functions of t and x, right? Right? And the other one are specified by specifying some relationship between the applied fields and the induced currents. Okay? And so now you need to sort of tell me what that relation is. Some relation. Okay, and so let's stick with just electric fields for now. We'll come back to it. Okay, and generically they're going to be weak. Good. Okay, and so what that means is that we're going to work to first order it. And what else? Let's also assume an isotropic medium. all of these you maybe relax, and we'll relax some of them as time goes on. Okay? And also, as we said, we're going to assume that the electric fields, at least very slowly on space and time, right, at least on the microscopic scales. So now we got to sort of write down J. So we write down all possible terms that are allowed consistent with symmetries. Okay. Or the symmetries which I desire my equations of motion to have. Okay. So the only field here is the electric field, and J is a vector. And so the only vector is E. So somehow J must be proportional to E and its derivatives, right? Its time derivatives. Let's skip the spatial derivatives for now. So, okay, and that's usually actually makes sense because the spatial scales of an atom are the time scales. It's non-relativistic, so typical time scales are typically much slower than the typical spatial scale. So the time derivatives of electric field end up being much more important than the spatial derivatives. We'll come to further later on. Okay. So let's just consider E as a function of t. Okay, and then the only kind of terms I can write down would be somehow these kind of things. Some numbers plus kind of. I don't know what I was going to E or something. Something like this. Okay, so that would be sort of a generic form of linear and constitutive relation that we could write down. Good. So, well, let's just say what it is. So first of all, we'll argue, each higher term is suppressed. Okay, so we only would keep the lowest ones. Okay, we'll come to that in just a second. Right. Kind of makes sense, every derivative will pick up derivatives of the slowly changing electric field. Okay, but let's just look at how this term is transformed on the time reversal. So, for instance, if I look at these things, right? So, let's say if time reversal is a symmetry. Equations of motion, right? Then under the map, E is even. Okay, so if E is even under right? Then the currents needed to be odd under time reversal. Or say it. So that's kind of so clearly, if I look at these terms here, these terms, if I have such a relationship between current and electric field, right, then that will break the time reversal of symmetry of the equation. Okay, good. Right. So that may not be a bad thing. I mean, so we're talking the first term, hopefully known as Ohm's law, right? That J is sigma E, right? And this Ohm's law sort of does break the time reversal symmetry of the equation of motion, right? So as you expect, these terms describe dissipative phenomena. So if you just are interested in the lowest, in very many materials, right, this sigma is vanishingly small. Okay. So for insulators, sigma is approximately 0. Okay. In which case, the dominant term in this expansion, right, is the second one. So get rid of those. Okay. Of course, if you're talking about metal, then sigma is not small, and it's the dominant term, and we basically neglect that. Okay. So let's for insulators, if sigma is small, right, then you're left with a kind of constituent relation. Say is chi times the time derivative of E, right, plus your higher order terms. Well, for metals, as we'll say. Get a new, right, and in terms like this, which involve time derivatives, will be unimportant. Okay, so yes, we sort of have a rough count. Yeah, go ahead.
Is this J you're using on the right side, what you were calling JMAT on the left side, or is this, okay.
Okay. So as we'll maybe justify a little bit further last time, the higher order terms will be suppressed by the ratios between the microscopic scales, the microscopic time scales, and the macroscopic time scales. Each higher term in this sort of derivative expansion will be smaller and smaller and smaller. Okay, so as a result, we'll stick with this simple form for dielectrics, and here's this simple form for metals. Okay. Good. Until you start talking about high frequency phenomena, okay, which is like waves in the media, okay. In which case, you'll need many, many terms in this derivative. I'll include them all, okay, and we'll talk about that at some point. Okay, stop there.